So in lecture we saw this idea of a game tree. We're going to look at a slightly more concrete example to see how you actually represent the game as a tree. So let's take the game of tic-tac-toe. And let's say it's X's turn first. If you ignore symmetry, so you ignore moves that are the same symmetrically, how many places could X move? So what if you ignore the moves that are symmetric? Like all corners are the same.
3.
3. So X could play in the center. On an edge. Or on a corner. So this is the beginning of our tic-tac-toe game tree, where each edge represents a possible move, and each node in the tree represents a game state, which in this case consists of what the board looks like and whose turn it is. So here it's O's turn. We're not going to draw out this whole tree because it goes on for a long time, but let's see what would happen if X played in the center. How many possible moves could O make in return? 2. So O could go on an edge or on a corner. In which case we would have this X in the center, and then O on an edge or corner. And so you can imagine continuing to do this for a long time, and eventually you would get to some endgame states. So you might have one, for example, where X wins, and a bunch of others, and maybe one where it's a tie. So it might be something like that's not. That's still not. Apparently it's hard to come up with ties on the spot. Okay, I think that's a tie. So then we could assign static values to these boards. So a static value is what you call the numerical score that you assign to each board. And there are 2 types of static values. There are endgame scores. So endgame scores are what you would assign to these boards when the game is over. So we might say that, let's call X the maximizing player. Then if X has won, maybe we'll say that board has a score of positive 1,000. Whereas this one's a tie, so we'll say that that's a score of 0 because no one won. So those are endgame scores, and you get those just from evaluating the board at the end of the game. And then there are heuristic scores, or heuristic estimates. And those are when we guess what the board, how good the board is at some point before the game is over. So a heuristic is just a rule of thumb, and we saw that term in search. So for example, we might say that in this board, it doesn't seem like anyone's doing particularly well. The game just started, so we might say this has a score of 0. Whereas if you have some board where it looks like X is going to win, but no one has won yet, we might say that has a score of, say, I don't know, plus 100. So that means that X is doing slightly better, but the game isn't over yet. So these are just estimates, and they might not be accurate, but they're a good way of guessing how good you're doing so far. And the act of statically evaluating is called static evaluation. So now we're going to look at, now that we have this game tree and we can see how you can put numbers at the nodes, we're going to look at this more abstract example like the one we saw in lecture and see what happens when you do the Minimax procedure. So Minimax is this algorithm where you have 2 opposing players. One wants to get the maximum score and the other wants to get the minimum score. So let's say that it's Max's turn first. And then Min's turn next. Then our goal right now is to figure out whether Max should go left or go right. And in order to do that, we're going to have to follow a recursive procedure. So that means that we have a base case and a recursive step. So the base case is when we get down to one of these leaf nodes, which could be the end of the game, or it could just be we're only willing to look 3 levels ahead, and then that's a heuristic score. So in the base case, we just evaluate the score, the current state. And then our recursive step is when we're going to look ahead at what our opponent might play in response to our move. So we'll look ahead at our opponent's counter moves. And this depends on whether it's Max's turn or Min's turn, so there are 2 cases. If it's Max's turn, do we want to return the minimum of the children or the maximum of the children? Max? Yeah, so it's what you would expect. We want to return the maximum of the children because Max wants the highest possible score. And then similarly, if it's Min's turn, then we'll return the minimum of the children. So this is pretty straightforward, but let's see how it works on this tree. So it's Min's. So we're going to start at the top where it's Max's turn. And in order to figure out whether Max should go left or right, we need to know the scores of these 2 children so we can take the max of them. So then we need to know the scores of these 2, and in order to know that, we need to know the scores below them. So we statically evaluate these, and we get 6 and 4. What does that tell us about what Max will do at this node? 6, because Max wants the biggest score. And then how about Max at this node? 8. So this is pretty straightforward. We're just taking the maximum score. Here we have 4. And here, the 2 moves are the same, so we'll just arbitrarily choose the left one for tie breaking. And now that we have those, we can see what Min would do at this level. I guess technically, according to this algorithm, we would do this whole subtree first. But what would Min do here? 6, because Min wants the smallest score. And then here, Min would get 2. So which way should Max go at the top? Left, because Max wants the 6. So notice that Max ideally would like to get this 8, but assuming that both players play optimally, Min won't ever let Max get to there. So this will be the Minimax path, which is the path the 2 players will take if they both play optimally. One question you might ask is what happens if the players don't play optimally? What if Max is a computer, but Min is a silly human who doesn't actually know how to play optimally? Then what happens is Max makes this move, assuming that Min is a rational player who will then go this way. And then Min goes this way for no apparent reason. Then it turns out even better for Max, and Max can get this 8. So I think in general, if your opponent is not playing rationally, you'll actually just do even better. Okay, so that's Minimax. But now we want to make that more efficient by not having to look at all of the leaf nodes. So then we have the alpha-beta optimization. So alpha-beta is not a separate algorithm, it's more of an add-on on top of Minimax. So basically what we'll do is we'll go through Minimax, but if at any point we discover that our score can't get any better than the best so far, we'll just stop looking. So we'll stop looking at a branch of the tree. score can't get any better. And the best option so far. So we're going to try that on this right tree using the same values of the leaf nodes. But this time I haven't written them in to indicate that we haven't actually evaluated any of these, and our goal is to evaluate as few of these leaf nodes as possible. So again, we'll recurse down to the bottom of the tree to where it's Max's turn. Also note that when this says max, that means it's Max's turn, not that we're taking the max of that level. So we'll have to evaluate this first node because we need some information. So we find out that's a 6. What does that tell us about Max's best guaranteed option at this node? At least 6. But we need more information, so we'll evaluate this one, and we see that it's a 4. So now that means that at this node, Max would get exactly 6. So what does that tell us about min there? Yeah, at most 6, less than or equal to 6. So we still need more information, so we'll recurse down this branch, and we see that this is an 8. So that tells us that here, Max would get at least 8. Do we not have enough information to know where min would go? Yeah, because min could go left and get a 6, or min could go right and get 8 or more. Min wants the smallest score, so now we know that min would go that way. This is equal to 6. And that also means that because min will never go down that branch, we can prune that branch. So this is pruning, also known as cutoff. And that means that we don't need to statically evaluate that node. So now we want to go up to the top of the tree. What do we know about Max at the top of the tree? Max will get a score of at least 6 there. So when we go down this branch and we recurse down to the bottom and we see a 4 here, which tells us that at this node, Max will get at least 4. Does that give us enough information yet to know what Max would do? No. So the way you can check that if you're not sure is you can imagine putting a very small or very large value in this node. So if you put a very small value there, like negative 100, then Max would get 4 here, and min would get 4 or less, and that's not enough information. Oh, wait, sorry, I think I did that wrong. Max would get 4 here, and min would get 4 or less. So then we would know we could go left. But if you put a very large value here, like positive 100, then Max would get plus 100, and min would get 100 or less if there's something better over here. So we still care about what's in this node. So we'll evaluate it and see that that's a 0. And you could also have done the same thing here with trying putting in a very large or very small number to see whether that value mattered, and you would see that in that case it didn't matter. Okay, so we have this 0, and that tells us that here Max will get a score of exactly 4. So what do we know about min here? At most 4. Now, do we have enough information? Yeah, because Max can either go down the left branch and get 6, or down the right branch and get 4 or less. So clearly Max should go this way to get a higher score. So now we know what the path will be at the end, and we got the same thing as there, which makes sense. But this time we did it in less work because we can prune off this branch, because we know that Max will never go down this branch. And we managed to completely avoid evaluating those nodes. So that saved us some work. Yeah.
Why are you pruning like above that node as opposed to like downward?
Here?
But you did expand the one side.
Yeah. So there are different ways of indicating this. In some notes, you will see it being crossed out here instead. So it doesn't really matter how you do that. But what Professor Winston did in lecture and what I'm doing here, this indicates that Max is not going to consider this branch anymore. Because Max has figured out that this entire branch would not be worthwhile.
Okay.
Any other questions? So now let's see what would happen. So this is a logical way to do alpha beta as a human. But if you were to have a computer do this, which you'll do in lab 3, then you want to keep track of these values alpha and beta. Professor Winston alluded to this in lecture, but didn't actually explain how it works, so we're going to look at that a little. So alpha will be a value to keep track of Max's best guaranteed score. That's these numbers that say greater than or equal to. So this is basically a lower bound on what score Max will get at the end of the game. And then beta is the same thing, but for min. So that's the less than or equal to numbers. So initially, we're going to initialize these values. If we don't know anything about what Max can get, what would be a lower bound on Max's best guaranteed score? Negative infinity, yeah. So we're going to initialize that to negative infinity, and that just means that initially at the beginning of the game, before we've looked at anything, we know that Max is guaranteed to get greater than or equal to negative infinity, which gives us no information. And then similarly, we'll initialize beta to positive infinity. So these values start out, if we were to put them on a number line, we start out with alpha way over there and beta way over there. And as we go through the alpha-beta procedure to get to this top node, the values will gradually get closer and closer to each other until, in this case, they'll converge at 6, because that's our final score. But if they ever cross each other, then that's a contradiction. And so then we'll prune. So if we ever have alpha is greater than beta, then we'll prune off that branch. And we'll look at an example of how that works. So I'm going to put up some...
Does each node have an alpha and beta?
Yeah, good question. So these get initialized at the top of the tree, and then they get passed up and down the tree. I think it'll make more sense when we look at the pseudocode. But yeah, it's sort of each node has a, I'd say each subtree has an alpha and beta because it's a recursive procedure. So if we look at pseudocode for this, let's say that we have some function alpha beta, which takes in the current game state, the alpha and beta values at that node, and the depth. So initially alpha and beta will be negative and positive infinity at the top of the tree, but then they'll get passed up and down the tree. The depth, we're going to say that that's 0 at the top of the tree. And then it just increases as we go down the tree. Here we have a depth of 1 and so on. So first we have our base case. And that happens if we're at the bottom of the tree. So if we reach the limit of how far we're willing to search. So we'll say if the depth limit has been reached. And it could be either because the game is over or because we're only willing to look, say, 3 levels ahead. In that case, we'll just return the static value of that board, so we'll just statically evaluate it. So that's our base case. Otherwise, we have our recursive step, which has 2 cases. Either it's Max's turn or it's Min's turn. So if it's Max's turn, then we want to look at all of the children of the Max node and recursively perform alpha beta on them. So for each child, we're going to update the alpha value. So the alpha value is keeping track of the best score that we found for Max so far. So it's going to be the maximum of our current best, and then the value that we get from the child in case that's even better. So So we'll call alpha beta on the child. Well, that function will take in the child node, the alpha value from this level, the beta value, and the depth plus 1. Because it's one level lower in the tree. And then we have our pruning condition, which is if we ever end up with alpha being greater than or equal to beta, then that's this contradiction. So we'll stop looking at future children and break out of this for loop. And that's our pruning step. And then at the end of this, we'll just return the alpha value. So then we're going to do a similar thing for min. It's almost the same, but I'm going to write it up anyway because it's slightly different. So if it's min's turn, then again we'll iterate over all of the children. But this time we're going to update the beta value. So notice that when it's Max's turn, we're only updating the alpha value. We're only changing what we know about Max's best guaranteed score. And at a minimizing level, we're only updating the beta value. So this time it'll be the min instead of the max, because min wants the smallest possible score. We pass in the current beta value, and then we call alpha beta on the child nodes. And then we have the same pruning condition. If alpha is greater than beta. And then we'll return the beta value. Okay, so now we're going to try this on a section of the tree. We won't do the whole thing. But if you want to see how the whole thing works, there's a demo that you can find here. There's an alpha beta demo on that page. So let's see what would have happened if we did this the computer way. So we would start at the top and initialize alpha to be negative infinity and beta to be positive infinity. We're at a maximizing level, so we're going to pass that down and take the max of these children. So we would first go down to this child and have alpha negative infinity, beta positive infinity. We continue recursing down, and we send the alpha and beta values to here. And then finally we get down to a leaf node. So this is a max level. So we're going to take so for each of the children, which are the 6 and this 4, we're going to compare our current alpha value to the value of that child, and then update our alpha value. So first we'll evaluate this child and see that it's a 6. So how does the 6 interact with these alpha and beta values? Yeah.
Well, it's Max's turn, so you need to, for the 6, evaluate it. Which one is greater of alpha, which is currently negative infinity, and since we've reached the base case of the recursion, the second part of that max just returns the value, so that's 6. So
yeah,
that means that we need to set alpha for that step equal to 6.
Yeah. So what she said is basically we're going to pass this 6 up and compare it to the alpha value, and we'll get alpha is equal to 6 because that's bigger than negative infinity. So now we have a better lower bound on what max we'll get. And that's equivalent to here where we wrote greater than or equal to 6 next to the node. So then we'll go and look at this leaf node and we see that it's a 4. We'll compare the 4 to the 6. Do we update alpha? No, because the 6 is better. So we take the max of 6 and 4 and get 6. So now we're done at this node. Now this is the tricky part. We're going to pass this 6, we're going to return the 6 in this return alpha step. But we're going to actually compare it to beta there, because what happened at this min level is we were looking at each of the min node's children and updating our beta value. So this alpha value that we return is going to become the new beta value. So that's really the trickiest part of alpha beta and the way the values move up and down the tree. But now that we have that, we can go down to this node, where we have alpha is negative infinity, beta is 6. This is for that node. And then we look at this guy, and we have 8, so we compare 8 to negative infinity. And we get alpha is 8. But this is where we have a contradiction. So now we have alpha is greater than beta. And what that means is, intuitively, now we're saying that if we get to this node, max is guaranteed to get a score of at least 8. But we previously found out that min was guaranteed to get a score of at most 6. So what this means is min will never let us go to this node. So even though max wants to go down that path, min will never allow it. So this tells us that we can, because we found this contradiction, we can cut off there and stop looking at the remaining children. Does that make sense? Okay. Are there any questions about that? Yeah.
Wait, can you say again why alpha gets propagated to beta and that, like...
This one?
Yeah.
Yeah, so that's the confusing part. So that's because at this min node, so we have this min node, and that corresponds to here where it's min's turn. And so we're updating the beta value by looking at each child. So we're looking at this child first. And whatever value this child returns, we're going to compare it to our beta value. But this is a max level, so it's returning this alpha value. So basically what happens is this max returns alpha, and this min compares it to its beta value. Does that make sense?
Yeah. I guess, like, why does it do that?
Yeah, so the non-intuitive answer is because that way the algorithm works out. I guess intuitively it's because, so earlier when we did it with the greater than and less than symbols, we said that since we know that max is going to get a score of 6 here, that tells us that min will get at most 6 here. And so that's equivalent to putting this 6 into beta, where we're saying that here min will get at most 6. So that's sort of how it connects to the greater than and less than signs. Are there other questions about this? It helps to look at the demo online and see how the alpha and beta values move up and down the tree, because it is a little confusing. Okay, so now we're going to let's look at a couple examples of cases where, in this case we got to prune a lot of nodes, but that's not always the case. So it depends on how the nodes are ordered. So I'm going to put up a tree, which is an example of worst case and best case alpha beta. So first, here's a worst case example where you don't get to prune anything. So if you have these leaf values, and if you have max going first. In all of our examples so far, we've had max going first, but it is also possible to have many go first. But if you have this, then you're going to end up with no pruning. So then alpha beta wouldn't actually help you at all, and you might as well just do normal minimax. Whereas in other cases, here's a best case example. You get to prune a whole lot of nodes. So just to make this point more clear, we're going to the best case example will be a tree with a branching factor of 3. And then you can see how there are really a lot of things that get pruned. So down here we'll have 4, 2, 2. These x's are going to be numbers that get pruned, so it doesn't matter what those values are. Whether they're really big or really small, they're going to get pruned. So you can try doing minimax on this, or alpha beta on this tree later to confirm that this is actually what you get. So here I just haven't drawn in all the little branches, so there are 3 leaf nodes on each of those. And again, max goes first. So you can see that there's a huge difference where here you actually get to prune a whole bunch of things. So now the question is, how are we able to prune, to affect how many things we prune? And the answer is progressive deepening with an additional thing called reordering. So first let's look at progressive deepening, which we saw in lecture. Progressive deepening solves the problem that this is really a depth-first search algorithm. So like here we had to look at the entire half of the tree in order to get information here. We still didn't know anything about that half of the tree. And so if you're going down to a really low depth, then you might run out of time before you get to return an answer. So what we want is an anytime algorithm. So that, for example, if you're playing chess on a timer and you have at most 5 minutes to make your move, if time runs out and you haven't had a chance to look at every single one of your leaf nodes, you'll still be able to return an answer that's at least reasonable. So basically, we're going to start by going to a depth of 1. So first we'll evaluate or perform alpha beta. Say minimax with alpha beta. To a depth of 1. Then we'll do it to depth 2. And we'll just keep doing that until we run out of time. And then we're also going to have this reordering trick so that in addition to progressive deepening, which is embedding this depth-first search algorithm inside a breadth-first framework, we're going to be able to increase our chances of pruning by reordering the nodes at each level. So after each level, progressive deepening. Reorder the node. To put the best or most promising moves first. So we're going to look at an example that uses both of these at once on top of the minimax and alpha beta that we already did. Is it okay if I erase this complicated tree? So let's look at an example, and we'll start by going to depth 1. Let's say that, again, it's Max's turn first. If we're going to with depth of 1, will we ever get to prune any nodes? Why not?
You have to see both of them to know which one's the max.
Yeah, because if we want to know, even if we had a whole bunch of possible moves, like if this was a chess game, then you might have, say, 16 possible moves. You don't know anything about a move until you've at least looked at something on that branch. So we won't get to prune anything at depth 1. So we'll just evaluate each of these nodes. We'll find out that that one's a 1, and that one's a 2. So Max is going to go that way and get a score of 2. So let's say that these nodes are called A and B. And then we're going to go to depth 2. Which of those moves is most promising? B? Yeah, because B is a bigger score. So for Max, the most promising moves will be the larger ones. So we're going to reorder the nodes, and we're going to say this time we'll visit node B first, because that's going to increase our chances of being able to prune something. So now we'll go down another level. And these were just heuristic estimates, so they might not be completely accurate. So when we go down to here, we see that this is 5. So what does that tell us about min at node B?
Less than or equal to 5.
Yeah, so here min will get a score of at most 5. We need more information, so we'll go here and we'll see that's a 4. So now we know that min will actually get a score of 4 by going that way. So what do we know about Max at the top? Well, Max will get at least 4. So it turns out our heuristic value at B was 2. And it turns out these are actually a lot better than that. So we thought here that B was a slightly better move, but it turns out it looks like if Max goes to B, then Max will get a really good score. So let's see what happens if Max went to A instead. We need to evaluate one of these, and let's say that this is 2. So far all of the numbers are looking better for Max than we expected. What does that tell us about min at A? Less than or equal to 2. Does that give us enough information to know where Max will go? Yeah. So Max could go left and get a 4, or Max could go right and get 2 or less. So we get to prune off that, and we don't have to evaluate that node at all. So let's see, how would we reorder the nodes if we were going to a depth of 3? We'll call these guys F, G, H, and J. So we're going to again look at this level, because in some cases, maybe it could have turned out that A was actually the better move, in which case we would want to switch them back and put A first. But in this case, which move looks more promising for Max? B, because it was still the better move there. So we'll keep B first and then A. So for min, the most promising move will be the one with the smallest score. So which node are we going to put there? G. So the tricky thing here is you might say, oh, well, H is the smallest score, so obviously we should put that first. But the thing is, H is a child of A. That's called shearing the tree. You can't change their parents. So we'll put G here, and then F. We don't know anything about J, so we're going to just leave H and J in the same order because it worked out well last time. So if it worked well last time, then it might let us prune again in the future. So that's the general idea of progressive deepening. You could continue doing this until you run out of time. Any questions on that? So, yeah.
So like and then like in my practice it doesn't take that much time to reorder the tree.
Yeah, not really. So also Professor Winston showed in lecture how it doesn't really take much time at all to do the deepening part where you're looking at each depth. I mean, it depends on your tree implementation, but I think it wouldn't be that computationally intensive to decide what you need to look at first. Other questions? So one thing we might ask is, what would have happened at depth 2 if we hadn't reordered this? Did this actually save us any work? So let's take a look at what would have happened. So here's the alternative depth 2 with no reordering. So then we would have node A first. So we would have gone down to look at the children of node A, and we would get a 2 there, which would tell us that min would get at most 2. Let's say that this one was also a 2, so then we would get equal to 2 there. And that would tell us that max at the top gets at most 2. We would need to look at least one node down here, so we would look at this one and see that it's a 5, which gives us min gets less than or equal to 5. Would that give us enough information to know where max should go at the top? I'm seeing yeses and nos.
The last thing was really small.
Yeah, so we can think about what would happen if this was really big or really small. If this was really small, then min would get some really small value here, like -10, and then max would want to go to the left. Whereas if this is a big number, then max would want to go to the right. So we do actually care what this value is. So we would end up having to get that value, find out that this is a min node, so that would be equal to 4. And then we would know that max actually wants to go that way. So we get the same path in the end, this path that leads to the value 4. But with the reordering, we were able to prune a node, whereas without reordering, we weren't able to. So that did actually save us some work. So to summarize what we did with games, we started out with the simple Minimax algorithm, and then we added alpha beta onto it, which allowed us to prune nodes to make it more efficient. Then we turned it into an anytime algorithm by adding on progressive deepening. And then if we add on reordering on top of that, then we can increase the number of nodes that we're able to prune. So that's basically how games work, also known as adversarial search.